Hello, I'm Stanley Bach, and this is the talk for Improved Geometric Path Enumeration for Verifying ReLU Networks. I'm going to be joining as an assistant professor in the fall in Stony Brook University, and this is also collaborative work with Hongdong Tran, who's a graduating student at Vanderbilt, and Taylor Johnson's group, who's also in Vanderbilt, and he's going to be also joining the University of Nebraska in the fall as an assistant professor. And Carrie Ann Hobbs is also on this work, and she's with the Air Force Research Laboratory. This paper is about neural network verification. So specifically, it's about the open loop neural network verification problem, where given some constraints on the input set, we want to prove properties about the output set. And so in particular, it's about evaluating improvements to the star set analysis method. So star sets are a data structure that encodes a set of states that sort of works really well for analyzing certain types of neural networks, in particular neural networks that are fully connected with ReLU activation functions. It also, there's extensions to convolutional neural networks and max pooling layers and things like that, but for this talk I'll be focusing on ReLUs and fully connected layers. So the reason they work well for this class of systems is that using star sets, you can exactly encode linear transformations and intersections in high dimensions. And so this means you can do exact analysis actually for this class of networks. So for example, given ranges on the inputs, I can tell you whether I can compute all the possible outputs in terms of sets, and then you can say, is a particular output possible by just doing set operations. So this is different than testing. It's sort of like exhaustive analysis. So ReLU activation functions compute the maximum of the input and zero. So if you look at the input-output space, it looks something like this, where the inputs are on the x-axis and the outputs are on the y-axis, right? So analysis is challenging primarily because these systems have both the chance to have negative inputs and the chance to have positive inputs. So it's really like a piecewise linear function. If it was an exact linear function, then you can analyze in very high dimensions. So it's not always difficult though. So for certain neurons in your network, if you could prove, for example, that the input is strictly positive, then you could show that the output is just identical to the input. So it's an identity transformation. So it's a linear transformation. And sort of likewise, if you can prove that the input is strictly negative, then this also means that it's a linear transformation because it's just a projection to zero. So really the difficult case is when you have neurons in your network that have inputs that can be either positive or negative. And so as I was mentioning before, with star sets, the nice thing you can do is if you're interested in exact analysis, you can split the set into two using an intersection operation and then sort of proceed recursively through the rest of the network. So the analysis sort of proceeds neuron by neuron through the whole network. So you could imagine if your layers are numbered from 1 to 5, and then at each layer you have 100 neurons, you could start with layer 0, neuron 0, and check if the inputs can be negative or positive. And then depending on which situation you're in, you can either proceed with just a linear transformation or split it into two sets. So in the worst case, you're going to be splitting exponentially, but in the sort of common cases, maybe you can get away with doing this and completing analysis. And so there's other options too, which I'm not going to really look at in this paper. So in particular, there's this triangle over approximation. So if you look at the original star set reachability analysis paper in FM 2019, they also talk about, instead of splitting, you can do over approximation. So here it's this is like the optimal convex relaxation of the ReLU in this 2D projection space onto a particular neuron. And so with star sets, you can actually encode this as well and do it efficiently too. And so the last sort of way to encode these ReLUs is what are called zonotope over approximations. And so compared with the triangle over approximation, there's actually more error. If you look at let's just say the area in this projection, the possible outputs for possible inputs, depending on the possible inputs, the zonotope is going to have more error, but the advantage is it's faster to compute. So with a star set, if you want to maximize a function over a star set, it's a linear programming problem. With a zonotope, maximization or minimization can be done in a simple loop. So it's significantly faster, but the cost is sort of you have more error. So I mentioned we want to do neural network verification, and exact analysis is possible. And so the way this works is that you analyze the inputs for each neuron and then compute the possible outputs. But as you might suspect, based on the strategy where you might split at each neuron, verification can actually take exponential time. So there's proofs that it's sort of NP complete. So if you have a network with 300 neurons, which is not a huge neural network, now you in the worst case could have 2 to the 300 sets. So it's obviously not manageable, right? You can't enumerate 2 to 300 sets using a sort of exact strategy. And then so the question becomes, okay, this is the worst case. Does it happen in practice, right? So just because a problem is NP complete doesn't mean we don't try to solve it. Like SAT solving is NP complete, or software verification maybe is undecidable in general, but we still have effective techniques to work on these problems. So in order to say whether this method is feasible in practice, you need to define what you mean by practice. What are the benchmarks that we run on? And so in this paper, we focus exclusively on the ACAS Xu system. So the ACAS Xu paper from 2017 is kind of a popular paper now. I think there's about 500 citations in just a couple of years. And what's neat about it is, they have analysis methods proposed that they use, but also they have a nice set of benchmarks. So it's a system that's supposed to prevent collisions among two aircraft. So by issuing turning advisories. And so the reason they're using a neural network rather than something else is that they had this sort of large lookup table of rules that you should follow. And they found out actually using neural networks, you get a nice compression of this. And so the motivation is, well, in avionics hardware, you can't, have, you can't have too much memory. So this compression might make a difference, right? But then the question is, okay, you've done the compression and it's not exact. Does it, still maintain safety of the system? So this is what the ACAS Xu system looks like sort of in simulation. So this is sort of closed loop simulations now of the system. And so you can see there's two aircraft. And so the one on the top is the intruder aircraft, and the one on the bottom are the own-ship aircraft that's running the ACAS Xu system. And depending on the initial state that you start in, you might get different sort of turn advisories, right? So this is a closed loop version. The open loop version just looks at, let's say a single point in here. What is the advisory that's issued? And then proving properties about the advisory. So for example, in this sort of head-on collision scenario, one advisory you might want to be able to prove that some advisory is issued. It doesn't give you the clear of conflict command. If there's this head-on situation, you should either turn left or turn right. And so that's actually, that sort of property is what's defined in this ACAS Xu paper. So more specifically, there's 5 inputs to the system, depending on the positions of the aircraft, the angles, and the relative velocities. There's a 300 neural network, fully connected layers with ReLU activation functions, and then it outputs 5 commands, and then the one with, I think, the minimum output is the one that's chosen as the actual output of the system. And then properties are things like what I mentioned, right? If there's this head-on situation, which you can define in terms of linear constraints on the inputs, then there should, the clear of conflict should always be the smallest. Basically, clear of conflict should never be the command that's issued, so it shouldn't be the smallest. So if you ever find a situation where the clear of conflict output is the smallest, that's a safety violation. And this is property 3 in the paper. So this paper is not about partial over approximation. This is sort of an additional thing you could think of where, instead of splitting or doing over approximation, why not do splitting on some neurons and over approximation on other neurons? That's definitely a good way to do it. But this talk is really about exact analysis. If you're interested in this method, there's another talk in VNN that you can look out for, which is one of the workshops associated with CAV. It's also not about perception neural networks that are sort of huge in size, where you may have millions of neurons, right? So there's another talk at CAV dealing with this problem too. So I encourage you to see that one. It's really just focusing on ACAS Xu and specifically what optimizations are possible for the star set technique. And so you can't really tell you whether it works or not unless I optimize the system. So what we've gone through is we've proposed a series of optimizations where we steadily have increased the performance from 10 to 100 times what the original star set approach was capable of doing. So let's look at the paper briefly. So if you open up the paper, it looks something like this. We've gone through the repeatability evaluation. There's a nice description of the algorithm that if you're interested in re-implementing, you can do that as well. There's descriptions of these data structures, sort of formally what I meant when I said a zonotope or what is a star set. And then there's evaluations where we look at different optimizations and we evaluate all, in this case, it's 180 different benchmarks on ACAS Xu properties 1 through 4. That are run on 45 different networks. So there's 180 benchmarks total, and then for different levels of timeouts, you can see how many properties you could verify. And so in the original work, the the proposed method was similar to a breadth-first search. There was a layer-by-layer analysis. And so we compared that with a depth-first search strategy, right? And apparently, as is sort of well known in model checking, when you do depth-first search, first of all, it's less memory intensive. So we can analyze several benchmarks that ran out of memory before. And it's also better at finding counterexamples faster. So we get a speed up now, and we can analyze, in this case now, in the 10-minute timeout, we can analyze over 120 benchmarks. So that's sort of like the first optimization. There's also this notion of how do you actually compute the minimum and maximum input at each neuron. And so there's several ways you can do this. So the first one is you could directly try to split the set and check for feasibility of the LP. And if it's infeasible, that means it's not, you can't split on that neuron. That's the copy pre-filter type here. There's bounds, which is just compute bounds using LP solving. There's sim, which is interesting because if you compute bounds with LP solving, you have to solve two LPs, a minimum and maximum. But actually, if you run a concrete simulation, you'll have a specific value that's either positive or negative. And if you have, if you know there's a real value that's positive, you could first try to solve the minimization LP. And if that's positive, then you know there's no split. So you can reject that, the branching with just a single LP solving. Zono bounds and zonosim are similar to bounds and sim, except they first do zonotope over approximation. And if the zonotope has if using the over approximation, the input is strictly positive or strictly negative, you can reject the branch with zero LP solving. So these are other ways you can speed up the analysis. And the next one is eager bounds computation. And so this is when you're going through layer by layer and a split is detected, you have a choice now. You could immediately split and proceed recursively, or you could keep computing for the rest of the layer. And so what this one does is it keeps, the eager one will keep computing LPs for the rest of the layer to get the bounds on all the other neurons before doing the split. And so that's useful because if you can reject branches for the larger set, like if using a larger set, you can tell that the last neuron in the layer doesn't split. Then after you split, you're going to get strictly smaller sets. And so then those ones no longer need to split either, and you don't need to solve an LP in each of those stars. So it's really choosing where to do the work. And so you see using eager now, we have a few more benchmarks we can analyze. And then there's also this domain contraction optimization that's described here. And so the idea here is with a zonotope, we can't do intersections exactly, but instead we can shrink the domain of the zonotope. So a zonotope is a linear transformation of a unit box in high dimensions. So you can't split it arbitrarily. If I have this linear constraint that cuts this box in half, I can't exactly represent that with the zonotope, but I can reduce sort of the box here by reducing the Ymax. And here I have sort of a smaller box, which is, it's actually a rectangle now, but it's okay because zonotopes are affine transformations of the unit box. So this is representable now, but now it's a smaller domain. So this increases the accuracy now of the zonotope over approximation. So ways to be able to, if I can make the zonotope more accurate, I can reduce the number of LPs I need to solve. And so there's different strategies we propose for doing that. In the paper, we also evaluate against other tools. So in particular, here's Marabo, which is the newer version of ReLUplex, NNV, which I think there's an improved version now as well. So this is the version as of January when we did our evaluation. There's R method, and then there's the Neurify tool. And so if you look at all of the properties, it looks like Neurify actually is better for most of them until you get to the end. So our tool is actually the first one we're able to analyze, I think, all of the properties before a timeout. Neurify actually times out for some of them. But actually, most of this benefit is just from property 1. So property 1 is sort of far from the unsafe set. And because we're doing exact analysis, we can't take advantage of that. We're not using the property, whereas Neurify is. And so if you actually remove property 1, that's what this plot here is on the right. You see that if analysis takes more than 2 seconds, our method is likely faster. So that's sort of kind of neat. We think this is a good result. And there's also a table of other sort of comparisons versus tools like ERAN. So ERAN, there was some script set up to work on property 9, and so we're able to outperform ERAN on that particular property too. And so the last thing I'll say about the paper is at the very end, there's a big table of every benchmark and how long it takes for every optimization level, as well as every tool. And so this is useful if you're developing a tool and you want to have some benchmarks. You can pick what's an easy benchmark. Like let's look, say, property 3, network 2.8. This one should be analyzed in 1 second or 0.1 seconds. So that's an easy benchmark. Or maybe you want something harder. You could look at network 3, property, or network 1.1, property 3. This one takes a longer amount of time to run. So this is very useful for tool developers working in the space as well too. So that's sort of a resource I could point you to. I think the last thing I'll say is that because it's exact analysis, we can actually visualize the reachable set over each layer. And so that's what this is showing here. This is ACAS Xu Neural Network 5.1 Property 3. And so what we're comparing is we did some random samples of the initial set, and then we're projecting things onto 2 dimensions. And so basically, if you look at the difference between the random simulations and the exact output set, you start to see some discrepancies, right? So like here, there's a large portion of the state space, or a large portion of the reachable set that's possible, but you don't get there using random simulations. But using our approach, you can actually, pick a particular target output and then generate inputs that get you there. So that's it. So our analysis, the sort of conclusion is star sets, you can do it 10 to 100 times faster on a lot of benchmarks. So it's sort of the jury's not out yet on which technique is fastest for these systems, and so there's competitions going on as well too. So in particular, VNN has one this year too. So I encourage you to come to that. So thank you for listening, and I'll be happy at the talk to answer any questions.